Right. Well, we only have a limited time today, of course, right? So we the we won't be able to finish logic gates obviously in just this short sitting here, right? So today I just wanted to cover universal gates. Um, the there are a few diagrams. I'll put them up just now. For you all basically have to learn it off, right? But what I want to go through with it is how you could, well, I mean, in the absence of being able to actually just learn it off, how you could actually derive the circuits themselves, right? Um, I mean, questions using the universal gates is very limited, because they could basically only ask you really to replicate what you already know, right? So I'll just run through the use of universal gates first of all, a little bit of the Boolean logic behind it, and then see how we could reconstruct some of the circuits there, right? Again, that's in the case if it somehow well, some people could just learn off something. Some people they need to actually see how it works before they actually be able to replicate it themselves, right? Now, universal gates, the concept of a universal gate is that, well, we have 7 basic gates we learned, right? So not and or XOR, and then the negation of those 3 will make 7 in total, right? Now, when it comes to the manufacturing process, right? The well, I mean, in terms of cost effectiveness and so on, you don't want to have it is not cost effective to produce 7 different chips, right? What is more cost effective is if you could produce 1 or 2 chips and then use those, well, I'm saying chips, I mean gates, right? Which are contained within integrated circuits called chips, right? We look at the 2 integrated circuits as well. So it makes sense to just produce a couple of them, and then you could use those couple to build on other gates, right? So for example, um, all of the logical operations could be constructed from only NAND gates alone. You could reconstruct all of the 6 other logical operations just using NAND gates alone, right? Similarly as well, you could do all logical operations with just NOR gates alone. So if you have a chip that is made with only NAND gates, you could reconstruct all of the other logical operations from that, right? So the first thing I want to point out to you all is how you could, I'll just deal with NAND first of all. NAND is the only one I'll go through in detail, and then the others I'll just ask you all to learn it all, right? So using NAND gate, right? Oh, I have this thing connected. Right. Yeah, press the record thing there, right? So universal gate. Right. Now you could use NAND, you could use NOR. But for example, if you just have AND gates alone, you cannot use just an AND gate itself to replicate the other logical functions, because the AND gate doesn't possess the ability to invert a signal, right? But by nature, NAND can invert a signal because NAND is the inversion of the AND gate. So it's built within it the ability to invert some input combination, right? They could ask you that. They could ask you to explain why it is an AND gate itself cannot be used to model the logical behavior of the other gates, and that's the reason why AND doesn't have the ability to invert an input signal, right? Or doesn't have the ability by itself, right? But however, though, you could take the NOT gate. Well, before I say that, the NOT gate itself, although that could invert an input signal, you cannot take just a single NOT gate to perform other logical functions, because it becomes difficult for you to logically combine more than one signal just with a single input gate, right? So, but however, though, you could use AND with or, I'm sorry, AND with NOT can perform functions, as well as, oops, or with NOT. Right? Right. So let me just run through some basics of Boolean algebra. Particular when it comes to inverting a logical combination, right? So let's say, for example, I have the AND gate, the AND behavior. AND behavior is like this. Matter of fact, sorry, I'm going to start with OR behavior. So OR behavior is this, right? You have your two input signals, A and B. You logically represent OR with the plus sign there, right? Now, I know you all would have done logic and truth tables and so on in pure maths in unit 1, right? So you would observe that, of course, the symbol is different in physics, okay? Not that you will ever really have to use it in particular, but anyway, whatever. O is represented by the plus sign in physics, right? Now let's say I could convert this O symbol here to an AND symbol using something called De Morgan's laws, right? De Morgan's laws is something from set theory. You all would have learned. You remember that if you have P union Q, and then you do the complement of that, it becomes complement P, complement Q, but when you complement the union, it becomes an intersection. I don't know if you remember that from set theory, right? So Boolean algebra is based kind of based on De Morgan's laws from set theory, right? Now I could convert this OR signal here, this OR combination into an AND combination by doing this, right? So what I'm going to do is I'm going to do this here. So I'm going to invert this here. So the bar over there means not, it means inversion, right? So of course I don't want to change the actual behavior of the gate itself. So if I invert once, I'm going to invert a second time. So if I invert the signal and then invert it again, it just reverts to what it was previous, right? So that's like a double negation thing taking place there, right? And then when I go inside here now, I just look at this alone inside here. I apply that to that particular logical function there. So this will become, so I have this negation over there. So I have to negate A, right? So I get not A or inversion A. I have to negate B, so I get inversion of B. And when I negate OR, I would get AND in that case there, right? So OR now could be expressed in terms of the AND function itself, right? So OR and AND, they could replace each other, but they wouldn't replace each other directly. You have to have the ability to invert the signal. So that's why I said here that OR and NOT could replace signals. Not OR by itself, but OR together with NOT could be used to model other logical operations, right? Good. itself there. Oh, sorry, I was on doing the wrong thing, right? So this setup I have over here is this here is uses and with the not function itself, right? Good. And I could do the same thing with the and as well, but I'm focusing on using NAND for now, right? As a matter of fact, I could show you all it with and as well. I could, the same way I could take or and express it in terms of and, I could take and express it in terms of or as well. I won't go through the details. And is the same thing as negation of A or B, like that there, right? So again, this is a way to express, oops, this here is a way to express or. This is or with not itself, right? Now I could take as well, well, that's a different point I was making there. Let me move on to into actually using universal gates itself. So what I've shown there is you could use and together with not to replace, or you could use or together with not to replace and itself, right? Now let me go on specifically to talk about about using NAND itself to replace all of the other functions. So using NAND gates alone. Right. So using NAND gate. So I could use a NAND gate to form an inverter. Right. Let me just remind you all of the truth table for the NAND function. So for the truth table for NAND function itself looks like this: A, B, and then A NAND B. So this is 0, 0, 0, 1, 1, 0, and 1, 1. Right? So if I have 0, 0, I will have 1. If I have 0, 1, I will have 1. If I have 1, 0, I'll have 1. And 1, 1 gives me 0. Right? That's in NAND truth table. You all should be familiar with that. Right? I want to focus on 2 rows of that truth table itself there. So the 2 rows I'm going to focus on is this here. And then I want to focus on this itself here. So according to these 2 rows of the truth table, so the output is low when not sure. I'll write this below. Right. So the NAND gate demonstrates the ability to invert an incoming signal, right? Now I'm not focusing on the whole, I've put down the whole truth table, but I'm really only focusing on those 2 rows that I have highlighted there. So you notice that when both inputs are low, the output is high, right? And when both inputs are high, the output is low, right? So that is classic inverter behavior. Inverter behavior gives you the opposite logical signal, right? So I could take an AND gate and perform this modification with it and get it to do exactly what a NOT gate does, right? So a NOT gate now could be created with a NAND gate. Try to draw this a little dish. So this is a NAND gate, right? So I want both inputs to always have the same logical value, right? Whenever they go into the NAND gate itself. To ensure that I always have the same logical value at both input terminals of this two input NAND gate, all I need to do is just have them connected to each other like that. So what I've basically done there is taken the two inputs and created one input from it, right? So whenever this here is logic 1, that there is also logic 1. Whenever this is logic 0, that there is logic, right? So I was able to take there a two input gate and create a one input gate with it, right? So whenever your both inputs are low, so if I have a logic 0 here, it means I will have 0 here and 0 here, and the output will then become logic 1. But these two zeros looking like that bubble thing there. Probably I should write this in a different color. So according to this here, if I have a logic 0 here, I will have 0 here and 0 here, which will produce a 1 output. So I have a 0 change, a logic 0 changing into a logic 1, right? So this here is the equivalent of a NOT gate. So that is how you create a NOT gate using just NAND gates alone, right? Well, using just a single NAND gate, right? So this is NAND here. Right, so that circuit above there demonstrates constructing a NOT gate just using a single NAND gate itself. So the important thing is that the inputs have to be tied to each other, and according to the NOT truth table, the inversion is produced whenever the both inputs have the same value and it is low, the output becomes high. Whenever the inputs have the same high value, the output is low, right? So that's a NOT gate from a NAND gate there. So it is just a tying of the inputs alone will produce an output like that, right? So that's not. I'm going to run through each of them in detail. I have all of them summarized in these drawings here, but I will put that up after, right? Right. So to produce AND operation from a NAND gate, NAND is already the inversion of an AND operation, right? We already discussed that when we did the basic truth table for NAND, that NAND is the inversion of AND. So if I want to use a NAND gate alone and produce AND operation from it, I just need to invert NAND operation. So let me put that down here. So NAND, oops. So basically, for me to construct an AND gate, I have to take a NOT gate and a NAND gate, sorry. So if I want to produce AND, I take a NAND gate and then I invert the output of the AND gate. Itself there, right? So that is the basics of how to get AND from NAND, right? But I already have discussed how you construct a NOT gate itself. So I could replace that NOT gate with this circuit on top here. So if I want to do that now, I'll just have to replace that with that there. So this will become the NAND gate that is taking the two inputs together, produce the NAND, and then that single NOT gate there will be replaced by another NAND gate there to produce the input, right? So this here is AND from NAND. Right, so I already showed you all this particular um, Boolean expression for or in place of, sorry, for and in place of or. So A or B is the same thing as this logical construction I have here, right? So if I want to use or reconstruct this from another logical set of steps, if I start off from the inside and work my way outside, the steps to basically reconstruct this particular equation is I have to invert A and I have to invert B as well. Then I have to combine them via an AND gate. And then when I get a result of that, I have to invert. Right? So those are the steps there of how I could have OR operation without using an OR gate. Right? So invert them individually, combine them via an AND gate, and then invert that final signal there. Right? So let me do that here. So I have, let's say I have my two inputs A and B, like this here. So I have A, then I have B, right? So the first thing I need to do is I need to invert both A and B. So coming out of A, I need to invert that, and I need to invert B as well. So I invert them individually, and then that there, those two then are now combined into an AND gate, and then that AND gate now is inverted itself, right? So this circuit here performs the OR operation without using an OR gate, right? So this is using AND and NOT logic to perform OR logic, right? So what I could do now is I already have, we already see how you could use an inverter, sorry, how you could use a NAND gate to replace an inverter, And then, of course, this AND gate as well could be replaced with two NAND gates like this here. Right? So I'm going to replicate this circuit here just using NAND gates alone. Right? So here, a single NAND gate could replace that inverter. A single NAND gate will replace that inverter here. And then if you just look at this alone here, this itself is a NAND gate itself. Right? So this is a NAND with the input side. This here is a NAND with the input side, and then this here itself, and followed by an inverter. That is how NAND behaves itself. So I need three NAND gates in this particular setup, right? So let me produce that here now. So I have to tie A and feed that into a NAND gate. I have to take B, tie the inputs B and feed that into a NAND gate. So this is an inverter, this is an inverter here as well, right? And this now collectively here will go into a NAND gate itself. Right, so we have not, we have or, we have and, right? The only two we need to talk, well obviously we have NAND itself. So we have NAND, not, and, or, nor is just the inversion of that particular circuit there. All I need to do is add a number So all I need to do now, if I want to construct NOR from NAND gates, I already have the OR construction over here. So all I will do is take the same circuit, and all I need to do is add an inverter onto the end of it, onto the end of it there, right? Good. Of course, the inverter itself could be constructed using an AND gate, so I'm not gonna put the inverter there, right? So to get the inversion of that there now, I just hook up another NAND gate with input side will produce the inversion of that there itself. So this is the OR part of it here, and this is the NOT part of it there, right? And of course, together would give you NOR operation using NAND gates itself, right? Good. Now, so the next two to discuss will be XOR and XNOR, right? Now, the XOR one, I will do that one in a little bit of detail. Now, the purpose of it is really just so that you would be able to replicate the circuit if for some reason you aren't able to learn off the drawing of the circuit itself, right? But anyway, so the next two might be a little bit tricky. So it's more likely you remember the circuit rather than remembering this discussion I'm going to engage in, right? Now, so we want to talk about, I will do XOR. Yeah, I will do XOR first. So XOR logic, right? The input signals, well, is usual combination 0, 0, 0, 1, 1, 0, 1, 1. XOR behavior is this here. If you have 0, 0, you will have 0. If you have 1, 1, you will have 0. And then over here, you will have 1, right? So to logically reconstruct what this particular gate is doing, it is doing, I'm just going to focus on where I have 1s there, right? So I'm not going to tie the inputs or anything like that. I'm just trying to logically understand what's taking place here, right? So when is the output of the XOR gate high? So for the output of the XOR gate to be high, you have to look at the input signals must be opposite, right? That's basically how you remember XOR behavior. So for XOR behavior with a 2-input XOR gate, you would have one input on, the other off. So the first one on and the second one off, or the second one off and the first one on. Is that the same thing twice? Whatever, opposite inputs, right? So the logical reconstruction of the XOR gate using the other basic logical functions is this here. So XOR is the same thing as A off and B on, right? So I'm talking about this row here. A off and B on. So A off is like negation A, right? And of course, well, I said the word and itself, so I use the logical and symbol there. So this is A off and B on, or A on, which is this row now, A on and B off. So this is here XOR operation in terms of and not operation itself. Well, it's actually and or and not operation. Good. So if I were to reconstruct this circuit here, I'll do it like this, right? So I will have my inputs like this. So I'm combining inversion of A with B via an AND gate. So this is how I do that. So to invert A, I have to place a NOT gate here. So what I'm doing here is I'm taking, hold on, I better erase that line. Okay, on it. Right. So I'm taking the inversion of A together with B, and I'm going to feed that into an AND gate. So inversion A together with B fed into an AND gate, like that there. And then I'm going to do now, I have to have another AND gate here, right? So let me take that AND gate now. Let me place it right here, sir. So I'm taking A, oops, sorry, I don't need to put it there. It's here. So I have inversion of A together with B in an AND gate, and then I have A itself in an AND gate as well, together with the inversion of B. Okay, that I come out too neat, but we'll try to draw it a neater thing. Like that there, right? So this AND gate here is A and the negation of B. This one below here is B and the negation of A, right? And then I'm going to combine those two outputs there now via an OR gate itself. Like that there, right? Now, I'm going to replicate the final circuit without too much explanation, right? Now, this circuit here is a kind of mirrored looking circuit, right? The final circuit using NAND gates alone is going to have a very similar sort of layout, right? So what I'm going to do is I'm going to do this here. This little part inside here itself, good. This here could be replaced with a NAND gate itself, right? This here could be replaced with a NAND together with a NOT, and the NOT itself is a NAND gate. Follow me, right? So I'm going to replace this here with a NAND as well, and in series with that NAND, I will have a NOT. Right? Now, when I take these two NOT gates now, feed that in to an OR gate, the equivalent of that there is a NAND. Good. So in the NAND version of XOR implementation, you have 4 NAND gates are necessary for that, right? And this is how the circuit looks. The final circuit is going to have the same sort of layout itself, right? So it's going to look like this. So I'm going to replace that one with a NAND. So I will have like a NAND gate kind of in the middle there. Then I will have 2 NAND gates on the top here. Easy way to remember it, right? A NAND gate below there. Then these here now will combine into a final NAND gate itself. So the 4 NAND gates are arranged like that, right? I have A being fed directly over there. B being fed directly over there. Good. But also too now, A and B have to go into this NAND gate over here. Right? And then the output of this NAND gate is shared. You should put this a little bit to the left. I'll shift this over here a little bit. I don't see why Ms. Gan had that chair by that time. By that door. Horrible drawing, right? Which is why I have the pictures, right? So this here, this type of layout here, kind of mirrored looking, if you turn your head horizontal, kind of mirrored looking there, is XOR implementation from NAND gates only. XNOR is a little less straightforward, right? XNOR, I will just give you all the circuit itself. And then no implementation of all of these gates, I will just give you all that to learn out itself, right? It's not always straightforward, the logic behind why the gates are constructed in that way itself, right? So this circuit here is XOR operation using NAND gate zone. Right? So basically, you could take a NAND gate, well, not a single NAND gate, but a series of NAND gates and you could replicate all of those seven, well, six other logical operations just using a NAND interval. So we have all of the reasons behind why the circuit is constructed like that and so on. I don't think you really need to know the reasoning and whatever too much. That's for your own understanding or whatever. Good. But at the end of it, what you really need to do is really learn off the circuits, is what you really need to do. Right? So that's this here. We bring those two, I'll bring up those two pictures there now. Guys, this, and this. Well, we already have all of the NAND implementation except for this one. The exclusive no is the only one I'm unwilling to go through that one in detail, right? So we would basically have all of these here already. We have the not, we have the and, we have the or, we have the no, the buffer. I ain't bothering with that buffer. The exclusive or. We just did that one. This one here, I want to draw this one here. This one here in elements, the exclusive no implementation using NAND. And then these here on the right hand side as well. What are you gonna do? That's all the time we have, right?